All right, I think it's time to start the session. Good morning, everyone. Welcome to the session 7C. This is the first session for Synthesis. We make sure you don't go to the wrong session. We have a very full agenda today. We have 7 presentations. It's a mixture of regular papers and tool papers, as well as a special report from the reactive synthesis competition. Yeah, the last presentation will run 10 to 15 minutes longer than the scheduled stop time. So it will have a small overlap with the breakout session. Hopefully they will start the discussion a little bit later. But anyhow, we will finish the session by, I think, 11 a.m. So yeah, just to make sure you don't leave earlier than you have to. So, and we have the thread on Slack talking about the discussing about each paper. So if you have questions, make sure you post to the corresponding thread. I will encourage you to post your question as early as you have to get a better chance to have your question answered, right? So you don't have to wait till the end of the talk. You can edit or delete the question later on if your question got answered, right? But you don't have to wait. Okay, so without further delay, let's start our first talk. The speaker is Christopher Han, and he will tell us about their work on realizing omega regular hyperproperties.
Hi, and thanks for tuning in to the first synthesis session. My name is Christopher Han, and I'm really happy to present our recent work on realizing omega regular hyperproperties, which is joint work with Bernd, Jana, and Leander. So in previous work, we considered the reactive synthesis problem of hyperproperties, meaning that we derived implementations directly out of hyperproperty specifications. And what makes hyperproperties so interesting and challenging is that they are not only reason on single execution traces, but they relate multiple execution traces to each other. And they gained a lot of attention recently due to security breaches like Spectre, Meltdown, or Heartbleed, which were information flow leaks, which are hyperproperties. Because if you have a look at the picture on the bottom right, in order to check for such a flow of information where high security information like credit card information leaks inside low observable output, so the idea is that we have to relate at least, or to compare at least 2 executions to each other in order to check out if there is some information flow going on. And the idea of this work was to use Hyper-LTL, which is a logic based on LTL by extending it with explicit trace quantification, which you can see here on the top left. And we can use then those trace variables inside the formula in order to make this relation possible. And the question that we are now asked in this work is, Hyper-LTL is limited to, on a trace level, is limited to properties that are expressible in LTL, and LTL cannot express omega regularity. So the question is, can we empower this synthesis procedure even more by considering hyperproperties and omega regularity? And what we would gain is with this is the full power of Büchi, and which also gives us the possibility to express powerful programming constructs. And one possibility to do that would be to just replace LTL with the QPTL formula. And just as a reminder, QPTL allows for this quantification of fresh propositions, which then can be used in the formula, which serves as kind of a marking, which gives us the power of omega regularity. what we gain by this is then omega regularity over n tuples, which is interesting in itself, but there are some properties that we could not express by just replacing LTL with QPTL, which are promptness properties. So properties where we require a common bound over the executions. Or another example is uniform termination, where we require a common bound, or where inside where the program has to, or the traces have to terminate. And in order to get this, for example, uniform termination, we need the quantification of our propositions in front of the trace variables, in front of the trace quantification. And this is exactly what we are studying in this work. So we study the reactive synthesis of omega regular hyperproperties, which are more expressive than just the combination of hyper and omega regularity. And we use the logic Hyper-QPTL, and in the theoretical part of the paper, we investigate the decidability. So we investigate the decidability of the problem, and we will see that there are fragments, really large fragments that still contain that contain promptness properties which still remain decidable. So the outline of this talk is as follows. I will just briefly go over Hyper-QPTL and explain the quantification of our traces and quantification of our propositions a little bit more in detail, such that we are capable of expressing expressing uniform termination and other promptness properties. And then we will go more deeply into the theoretical findings of this work, especially check out which fragments of the logic remain decidable and which not. And then I will also show you that we have implemented this in a prototype where we were able to synthesize really non-trivial arbiters that respect promptness. Where such an specification also contains this mentioned alternation of the quantifiers. All right, so first of all, the trace quantification, which is the logic hyper-LTL. And you can see the same example here on the top again, which is we have all executions must have the light on at the same time. And the idea is here that we state that for all traces pi1 and for all traces pi2 on every position, if on is holds on the trace pi1, it also has to hold on the trace pi2 and vice versa. And with this mechanism, we can now, which you can see on the bottom, we can relate now those traces to each other. And while this is an easy example, you are not restricted to the same position or the same proposition. So this the indexing can happen on different positions or the relation can happen on different positions and different propositions, meaning that we can also express very interesting policies like non-interference, observational determinism, or symmetry, or robustness, for example. And now to the second ingredient of Hyper-QPTL, which is quantification over propositions, which gives us this omega regularity. It is known that LTL cannot count, it cannot express a counting language. And such a counting language is displayed here on top, where we require that a program terminates, so this halting symbol appears just exactly after an even number of steps. And in order to check this or to ensure this with a QPTL specification, we can use those propositions as markings. So we quantify fresh over a new proposition Q and require that Q holds on the first position. So you can think of this as a new trace which is not in the system. And then we require that the second position is not marked, and the third is marked again, and so on. So every second position is marked. And with those markers now, we can use them in order to make sure that now, if we are in a position on the top trace, if we are on a position where we would like to hold on the next step, then this is either a position where we already have terminated, which is the left side of the disjunction, or it is a position that is not marked, so meaning it is an even position. And with this conjunct, and then we can add the conjuncts that we will eventually terminate, and if we terminate, we terminate in all positions. And with these, with this formula, then we can ensure that we can just express this language displayed on top, which is not possible in LTL. And these are the two ingredients for Hyper-QPTL, and the question is now just how do we combine them? And the first possibility would be to first quantify over the traces, followed by the quantification over propositions. And what we would gain by this is like only omega regularity over n tuples, which is interesting in itself, but not sufficient to express those promptness properties that we were talking about in the introduction, or these uniform termination properties. So what we instead would like to have in order to express this is the true mixing of the quantification over traces and propositions. So we allow for any quantifier order. So this gives us now a lot of interesting fragments. And now I would like to go a little bit more into detail. And the first fragment is the fragment where no universal trace quantification is allowed. And this allows for a kind of a straightforward reduction to QPTL realizability. And the idea here is that we are just replacing each existential trace quantifier with quantification over propositions, which is done here on the first conjunct of the formula. We just replace every pi I with those quantification over propositions. And the second conjunct is just a technicality where we just make sure that we're only allowing actual strategies of the strategy tree. And the second straightforward fragments are where multiple universal trace quantification is allowed. And because it is known that multiple trace quantifiers allow for the encoding of distributed architectures. And as just a reminder, the distributed synthesis problem is that we are not only deriving one implementation, but we are deriving multiple implementations for different processes. And for this, we also have not only the specification as an input, but also this artificial input of the distributed architecture, which defines which input, which process depends on which input, and so on. And since it is known that we can encode such distributed architectures inside even Hyper-LTL, there are decidable architectures with no information forks, and there are undecidable architectures with information forks, where an information fork means that there are that there are at least two processes which are differently informed, which leads to undecidability. And so these are exactly the fragments that represent these kind of architectures, where either the ones that can be linearly ordered, which is why it is called a linear fragment, or where an information fork is happening, which cannot be linearly ordered, which is the nonlinear undecidable fragment. So this now I would like to go on with the more interesting fragment, which is the single universal trace quantification fragment. So this is the class where those promptness properties and those universal those promptness properties fall into. And the idea here is a reduction to the distributed realizability of QPTL, but where we have to make sure that we don't use a distributed architecture with an information fork. And this is a little bit more advanced, but more complicated, but I would like to briefly give you the idea. And the idea of the main lemma is that we are using two processes where one process has as outputs the copies of atomic propositions that are indexed with the existential trace quantification, and this process just determines the choice of the existential quantifiers. And then we use this straightforward architecture, just a straightforward process P2, which receives inputs and produces the outputs for the synthesis problem. And this fragment actually remains decidable, where all those uniform termination properties fall into. And what we also show is that this fragment is tight, meaning that when we have an for all exists quantifier alternation, either just with traces or with propositions, we can encode post-correspondence problem. And this is mainly due to the fact that we have this power of for all exists at our hand that we can use there. All right, so these were some of the theoretical findings, and now I would like to also show you our experimental results. So we implemented a bounded realizability and bounded unrealizability procedure, and we were able to synthesize prompt arbiters directly out of such hyper-QPTL specifications. And yeah, it was implemented in BOSI, and it's a bounded synthesis tool. It reduces the problem to SMT and then utilizes set3. So, and on the top right, you see again this arbiter 2 prompt specification, where we required that one process has to act prompt, where one grant has to be given prompt, and where this full promptness instance here means that both grants for process 1 and process 2 have to be given prompt. And then we were able to synthesize an arbiter of up to for 3 processes, and we started timing out for process arbiter. All right, so I would like to, with this slide, I would like to conclude. So I showed you Hyper-QPTL, which can express omega regular hyperproperties, and especially promptness properties and uniform termination properties. And I also showed you some of the theoretical findings in this work, that there is still a large class of properties for which the problem remains decidable, like promptness and bounded termination. And I also showed you some of the experimental results where we were able to synthesize prompt arbiters. And the interesting thing here is that research of LTL research, SMT research will immediately carry over to the synthesis problem, or to the scalability of the synthesis problem of Hyper-QPTL. And with this, I would like to thank you, and I'm happy to take questions.
All right, thank you, Christopher. So let's see, we have a long discussion about video quality. I guess the first real question is from Muhammad Osama Sada. And the question is the tool available for real life problems? What are its limitations?
Yeah, so we can make the implementation available. And well, the problems or the limitations are inherited from from synthesis limitations that are around for LTL and for Hyper-LTL as well. So we are not able to synthesize huge systems, but I think the main contribution of this work is not the prototype, but the finding that we can actually, without the help of artificial yeah, things like prompt semantics can just encode this inside the specification and still be able to synthesize things. Yes, but we can make the code available. This will be no problem.
Okay, thanks. Yeah, I think I actually have some a follow-up question about the property. You talk about the, what's the name, universal termination, or yeah. So, but is there some property related to security or some real world properties that people are interested in, or it's just an artificial property that you need omega regularity and the hyperproperty?
You mean now for like this combination, or?
Yeah.
Well, I think in every property that you can imagine where you need a common bound over all traces, it also can be like a common bound in an information flow policy that you would like to have over traces. So I think this is not just an artificial problem or an artificial example here, but in every yeah, you can imagine every kind of interesting security policies where you need this quantification before reasoning over relations of traces.
Okay. Okay, let's answer the last question from Xu. Have you considered introducing templates or sketches to improve the scalability?
So the idea is here to somehow, if I understand this question correctly, to give a main sketch on how the system could look like and then fill in the blanks. And if this is the case, then no, we have not considered this yet. But this is like an ongoing research in LTL synthesis, for example. And I think the cool thing here is that since it all boils down to SMT, to LTL synthesis, that research in this area, which is going on in this community, that it translates to our findings as well. Yeah.
All right, so we have more questions, but we have to move on to the next talk. So feel free to continue the discussion offline. Thanks, Christopher. So the next talk is from Mahmoud Khaled. He will talk about the tool called Amethyst. Jingbo, will you start the video?
Hello everyone, I hope you are all doing well and healthy. I'm Mahmoud Khaled, and today I will present the tool paper Amethyst, Parallelized Automated Controller Synthesis for Large-Scale Stochastic Systems. This is a joint work with Abul Fadl Lavai, Sadiq Sudiani, and Majid Zaman. Large-scale stochastic control systems arise in many applications like traffic networks, self-driving cars, delivery drones, vehicle platoons, and power grids. Using automated synthesis of controllers, one can design correct by construction controllers for such safety-critical systems. We can also handle high-level logic specifications, such as those expressed as LTL formula. Unfortunately, most of the approaches of automated controller synthesis suffer high computational complexity. One traditional approach to automatically design correct by construction controllers for stochastic control systems is to use approximations. Given a model described by a system of difference equations with stochasticity, disturbance, or noise on the states, one constructs a Markov decision process to represent the model. Then, given a high-level specification like safety, reachability, or reach avoid, one computes a formally correct closed-loop controller to satisfy the specification. This approach is unfortunately complex and suffers a phenomenon known as the curse of dimensionality. That is, the complexity grows exponentially with dimension of systems. So the question of interest is how to efficiently design controllers for large-scale stochastic control systems satisfying high-level logic specifications. In Amethyst, We propose a solution to employ high-performance computing platforms together with cloud computing services to mitigate the state explosion problem. The main contributions are that Amethyst introduced novel data parallel algorithms to construct finite Markov decision processes as approximations of control systems. Amethyst introduces parallel algorithms for synthesizing discrete controllers using the constructed MDPs to satisfy safety, reachability, or reach-avoid specifications. Unlike many existing tools, Amethyst accepts bounded disturbances and natively supports both additive and multiplicative noises with different distributions, including normal, uniform, exponential, beta, and even custom distributions supplied by the user. We briefly introduce the parallel algorithms implemented in Amethyst. Complete details about the parallel algorithms, comparison with serial ones, and discussions about the complexity can be found in the tool paper. One parallel algorithm is designed to construct an MDP as an approximation of the original system. There, we sample in parallel the continuous state and input spaces of the control system. Then, for each input state pair, we launch parallel threads to compute the probability of reaching other states. Finally, the transition probability matrix T hat of the constructed MDP is maintained as a distributed data container. The second algorithm is for the parallel design of the correct by construction controller. Controller synthesis is done via iterative computation of Bellman equation in standard dynamic programming. Within each iteration, the parallelization is applied to the lowest level of computation, that is, the matrix multiplication in Bellman equation. We also made some improvements to the parallel algorithms. First, to reduce the memory required for the transition matrix T hat, we allow the user to set a cutting threshold for the probabilities. This introduces sparsity in T hat, and Amethyst identifies it and uses it to reduce the memory. Second, on the level of controller synthesis, we allow the user to switch on a feature for the on-the-fly computation of T hat, which eliminates the need for a memory to store T hat and significantly reduces the required memory. This, however, comes with the cost of repeated computation of T hat, but still gives the user the control over the trade-off between computation time and memory usage. Amethyst is implemented in C++ and OpenCL. C++ is used for serial and utility codes. OpenCL is used for data parallel and low-level parallelism. We implemented Amethyst on top of P-Faces, an acceleration ecosystem with support for formal methods in control. Amethyst is open source and can be downloaded from our repository in GitHub. You can start using Amethyst immediately with the provided Docker file or build it using the provided build scripts. All information can be found in the README file in the repo. Compared with other similar tools, Amethyst is the only tool to support hardware platforms like GPUs and hardware accelerators and clusters of them. With its parallel algorithms, it scales better and utilizes all available resources. Unlike others, we support nonlinear dynamics, reach-avoid specifications, and multiplicative noises. We give the user the choice of the underlying distribution of the noise, including the ability to supply customized ones, and we also support disturbances in the difference equation. In the paper, we presented an example to show the capabilities of Amethyst. Consider a two-dimensional robot described by the shown difference equations with both noise and disturbances. The robot is supposed to reach some target set in the state space, shown by a blue box, and avoid an obstacle in the middle, shown with a red box. The problem is provided to Amethyst as a text file describing the dynamics and the specifications. Amethyst can solve the problem in fractions of a second. Due to the nonlinearity in the model, other tools cannot solve the problem.
Examples in Amethyst are described by configuration file. Here is the configuration file we use to describe this 2D robot and to do reach avoid. Let's have a look to the configuration file. In the configuration file, we give a name to this project. We provide information about the states. We also provide information about the dynamics of the system. Here is the difference equation, information about the noise, and the specification. Now we run it. The time taken to solve this problem on this CPU is 46 seconds. If we run the same example on the last GPU in this machine, we will get different computation time. As you see, this GPU is much faster than the CPU, and the problem is solved in much less time.
We also compared Amethyst with other tools for a wide range of case studies. We used 6 machines ranging from local ones to machines in Amazon AWS cloud. They include different number of processing elements, ranging from 8 CPU cores to around 5,000 GPU cores. The results show that Amethyst overperforms all similar tools with orders of magnitude. We pick one particular case study and show the scalability of Amethyst. Note the 2D robot example shown as a green row. With the CPU machine having 8 cores, the problem is solvable in around 50 seconds. With the GPU having 5,000 cores, the problem is solvable in fractions of a second. Finally, I would like to mention that this work was supported in part by the H2020 ERC starting grant out to CPS. Thanks for your attention, and I will be happy to answer any questions.
Okay, thank you. I haven't seen any question in the thread, so please post your question if you have. I have a question about the hardware configuration. It needs to be explicitly given by the user, or you have some mechanism to detect the hardware and figure out which resources are available and tune your algorithm. Yes.
So actually, Amethyst is implemented on top of pFace's acceleration ecosystem. This acceleration ecosystem takes care of detecting the underlying hardware automatically. So once you install it in a machine, it detects all CPUs, GPUs, or hardware accelerators installed in this machine. Then it provides support to the kernels, which is, in this case, Amethyst is running as a kernel on top of pFaces. And the threads required by Amethyst to execute is managed by pFaces, and it takes care of executing them over all available CPUs or GPUs or whatever hardware the user specifies.
Okay. Okay, thanks. All right, we don't have other questions, so let's move on to the next talk. It's another tool paper presentation about Code2Inf, a deep learning framework for program verification. And we have two speakers for this talk, Shujesi and Aditya Naik.
And I'm Aditya Naik.
Today we are going to present Code2Inf, a deep learning framework for program verification. We are inspired by many recent success of reinforcement learning, especially deep reinforcement learning, which outperforms human experts on challenging strategy games. We observe very interesting connections between gameplay and program verification. Specifically, the grammar checker used in program verification are very similar to rules and environment in gameplay. Such an observation motivates us to apply deep reinforcement learning to program verification. However, there are many new challenges here, particularly in two aspects. First, representation learning. Unlike an image, programs are structured data whose size varies a lot. It is unclear what could be a good neural architecture to represent programs, for which we leverage graph neural networks that are derived recently. Secondly, reinforcement learning. Actions for games are simple, usually fixed and finite, and its reward is also rich. However, for program verification, actions are given by context-free grammar, which are complicated and potentially infinite. Furthermore, the reward is extremely sparse, which is almost always zero, actually. To make the learning process efficient, we propose a smooth, count-example guided reward design. Here's the overview of Code2Inf. It takes a piece of code and invert grammar as input, then interacts with an event checker, and improves the policy upon count examples given by the checker, eventually converge to a correct proof. Code2Inf can be easily extended to solve very different tasks, for instance, constraint horn clause solving. In general, as long as there's a checker and a grammar specifying the syntax of candidate solutions, Code2Inf could turn that checker into a solver. Let's zoom in a bit and see how we represent the programs. The goal is to turn a program into high-dimensional vectors, also called embeddings. A straightforward way is to view programs as a sequence of characters or tokens, then plug in the sequential model, often used in natural language processing, which however works poorly here due to issues like out of vocabulary or lack of structured information. A much better and intuitive way is to view programs as graphs, for instance, control flow graphs or data flow graphs. Then we can leverage a neuron graph embedding to turn a graph into a collection of numerical vectors. Each vector or embedding is associated with a node of the graph, which captures the local neighborhood structure information. Note that the structure information is really independent from variable names. Here's an example of inverted grammar, where S is the start symbol. Unlike the normal context-free grammar, there's a special causal symbol here called a placeholder. When the generation reaches a placeholder, the attention mechanism is used to concretize it by choosing the most relevant variable or constant in the program according to the current neuron context, which is a combination of program embeddings and partially generated invariant. To be able to handle nonlinear loop invariant, we only need to introduce a nonlinear operator in the grammar without changing anything in the backend. Let's look at the backend code twin. Could we sample a candidate solution according to the given grammar? An optional quick feedback is given based on the syntax, which we call early reward. Then the candidate solution will be forwarded to the checker. The checker returns either a success, which indicates a correct solution is found, or failure. When that happens, a count example is usually provided. We derive a continuous reward based on these count examples, which is essentially a quantitative measure of incorrectness. More specifically, we use a fraction of count examples satisfied by the current candidate solution as a continuous reward. This significantly improves the learning efficiency.
The experiments that we conduct showcase the capability of CodeTwinf to solve two different types of tasks. We use CodeTwinf to synthesize loop invariants and consider 133 C benchmark programs from the Cycles competition. We compare CodeTwinf with 3 other tools, C2I, ICT, and LoopInfGen, the latter two of which were the winners of the 2016 and 2017 Cycles competitions. We also use CodeTwinf as a CHC constraint solver and consider 127 CHC benchmarks. We compare CodeTwinf with spacer and data-driven CHC for this case. We compare the performance of various loop invariant synthesis tools by comparing the verification cost, that is the number of Z3 queries called by each tool, versus the number of programs verified within the corresponding cost. We see that CodeTwinf outperforms the other state-of-the-art tools significantly. In the CHC constraint solving task, we see that spacer solves 112 benchmarks, data-driven CHC solves 118, whereas CodeTwinf solves 99 from the 127 benchmarks that were considered. 94 of these were solved by all 3, and the 5 additional benchmarks solved by CodeTwinf were nonlinear instances unsolved by other tools. We come to the case study on naturalness, and we see that the solutions found by CodeTwinf in both cases are simpler and more natural as compared to the solution found by spacer, and thereby they are more understandable. The same goes for the solution found by data-driven CHC. To extend CodeTwinf, we must implement 3 components. The first is the front end, which is supposed to convert the program into a JSON graph representation and feed into CodeTwinf's representation learning. We also implement the grammar, which will define the syntax of the solution for the program and will be used by the reinforcement learning. The third component is the checker, which will check the candidate solution and return a counterexample if failed. In conclusion, we present CodeTwinf, an end-to-end learning framework for program reasoning tasks. It allows for automation and alleviates the need to hand engineer search heuristics. It allows for flexibility and easily allows CodeTwinf to be extensible to new domains by simply adding components. It allows for adaptivity and adapts search strategies within and across instances and can easily be used to transfer knowledge between instances of similar structure. And it allows for naturality, which produces more natural solutions. Please try out Code2Inf at our website. Thank you for listening to this presentation.
Okay, sorry, I forgot to unmute myself. Okay, thank you, the speakers. We have the very first question. Oh, sorry. Yeah, the first question is from Kuldeep Mew. And the question is, how does the tool work when compared to CVC4?
Okay, yes. Yeah, I'm not sure the question is if we replace this three with CVC4 or just the entire framework compared to CVC4. I would say in general, maybe compared to in SMT solver is here the heuristic is really controlled by a neural agent, basically the neural agent in charge of every decision. Well, for manually designed SMT solver like CVC4, these three, there's some manually designed search heuristic which is fixed and wouldn't adjust during the for each problem instance. Yeah, I would say that that's a main difference. In terms, say, if we if the question asks if how do we encode the combine the two with these three versus CVC4, we haven't really tried out yet. But the framework itself doesn't matter much about the online checker. As long as the checker could give a kind of example. Yeah, it is.
I think this question is more about comparing to CVC4 as an invariant synthesizer, as CVC4 is a winner of last year's SYNTCOMP competition. So you compared with yeah.
Okay, I see. Yeah. The evaluation is performed on the 2018 tasks. So yeah, but then we haven't we haven't considered CVC4 by then. Yeah, it's
okay.
But I would say okay. We do some study after the the evaluation. I think CVC4 their behavior well is it target on certain have a much better innovation strategy. So yeah, I would say CVC4 will be definitely faster because here even though we argue that the number of queries is much less than those STLR solvers, but if you look at the time, lots of time really spent on the training part. So here the really interesting part is you view this kind of reinforcement learning process as a smart way to search, because basically here each agent really starts from random weights. So yeah, obviously in terms of absolute time, it's not comparable yet.
All right, thanks. Let's answer one more question from Elizabeth Paul Green. The SYNTCOMP invariant benchmarks are unbounded mathematical integers. Could you also handle bounded integers as in C code with your technique?
Currently, technically, sure, of course, we can, as long as your grammar could specify those constraints and the checker can check it. Yes, it should be able to handle. But kind of our evaluation, we consider those unbounded integers. So yeah, it remains to see how good the performance when we handle those unbounded integers. Yeah. But technically, that won't be an issue.
Mm-hmm. All right, thank you, the speakers. We have more questions on Slack, and please take a look at the talk.
Thank you.
Okay, so the next talk is about maximum causal entropy specification inference from demonstrations. And the speaker is Marshall Wazik-Charlotte.
Hello, my name is Marcel Vasquez-Charlotte, a PhD candidate at the University of California, Berkeley. Together with my advisor, Sanjit Sesha, I have been working on the theory and tools for communicating formal specifications through demonstrations. In this talk, I will discuss our recent work on inferring specifications from demonstrations using the principle of maximum causal entropy. To begin, I'd like to start with some high-level motivation. At the highest level, this research aims to enable human-robot interaction. To that end, physical demonstrations are a natural way to express tasks and relay intent. However, in the context of formal methods, it's often unclear how to best leverage this information. In particular, within the context of formal methods, one often presumes the existence of a system and a formal specification. For example, verify the system on the right satisfies the specification on the left. However, in practice, this is rarely the case. This is because, even for experts, writing down a formal specification can be non-trivial and time-intensive. This is why we've been interested in developing techniques for inferring formal specifications from demonstrations. However, working with demonstrations comes with its own set of challenges. To start, demonstrations are often noisy and contain errors, either due to user mistakes or stochastic transitions. Furthermore, demonstrations are often unlabeled, since they come from logs, or, in the case of real-time collaboration, may not yet be over. Next, demonstrations are often given within some context. For example, one might provide a natural language description of the task. Here, avoid red while reaching yellow. Or there may be a task-specific prior based off the domain. Finally, and perhaps most importantly, demonstrations are often ambiguous and do not uniquely define a specification. However, our aim is to provide a partial ordering between specifications so that one can say which of the two specifications is more likely. For example, did the user intend to avoid lava? Is it more likely that they were trying to avoid lava or not? To recap, demonstrations are noisy, unlabeled, contextual, and ambiguous. Thus, our goals for this work are to have a noise-resistant, unsupervised, and Bayesian method for inferring formal specifications from demonstrations. To this effect, our contributions are as follows. Formulate a robust inference method using the principle of maximum causal entropy. Compared to our prior work, this method supports stochastic environments. Next, we provide an efficient implementation based on binary decision diagrams. Finally, we provide an experimental validation of this method. The structure of this talk mirrors the contributions. In particular, we'll start with the problem setup, provide a naive problem formulation using the principle of maximum causal entropy, provide a more efficient encoding using binary decision diagrams, and wrap up with an experimental validation. To begin, let's set up some basic definitions. We're going to assume that there's a fixed set of states and actions. For example, in this grid world, states are positions, and actions are attempts to move up, down, left, and right. More generally, we're going to assume that we're operating in a Markov decision process. A trace is a sequence of states and actions. For simplicity, we're going to assume that all traces are the same length, tau. A Boolean specification, then, or a trace property, is a set of traces. In practice, one doesn't typically describe the set of traces in a specification, but rather one provides an abstract description in a formalism such as logic, automata, or epsilon optimality. Furthermore, it's important to note that Boolean specifications don't provide an a priori ordering between traces, and it is in this way that demonstrations differ from normal labeled examples. In particular, a demonstration of a task phi is an unlabeled example where the agent tries to satisfy the specification. For example, in this image, we see an agent attempting to reach the yellow tiles while avoiding red tiles. However, due to wind, the agent slips downward and enters the red tile. What's important is that even though this is a negative demonstration, the actions and the implicit dynamics probabilities provide enough information to realize that the agent did not intend to enter the red tile and was most likely trying to reach the yellow tiles. Here, agency is key. So is a notion of an action. And in particular, the dynamics plus the actions induce an ordering based off of the success probabilities. Once we know the dynamics, we can say that this left trajectory and control policy is better than the right policy. We're now ready for an informal problem statement. In particular, we're going to assume that there's a demonstrator and a learner. And because of the way that demonstrations work, we can ask, is it likely that the agent would generate a given set of demonstrations given a particular abstract task? In particular, we're going to assume that the demonstrator or agent is operating in a Markov decision process while trying to satisfy some unknown specification. And then, given a sequence of demonstrations, and a collection of specifications, we're going to ask to find the specification that best explains the agent's behavior. In order to do this, we're going to need two ingredients. First is we're going to need to know how to compare specifications, and that's going to be the primary focus of this work. The second ingredient is a way to search for likely specifications, and we're going to leave that as future work. We are now ready for a naive problem formulation. In particular, we're going to do so by reduction to inverse reinforcement learning. As a reminder, in inverse reinforcement learning, one assumes that an agent is acting in a Markov decision process and is optimizing the sum of unknown state rewards. In inverse reinforcement learning, one is given a series of demonstrations and asks what reward R best explains the agent's behavior. The problem is, there's no unique solution posed to this problem. A common idea, and a very successful idea, in inverse reinforcement learning has been to disambiguate using the principle of maximum causal entropy first introduced by Zbart in 2010. Now, while I don't have time to formally go into all the details of the principle of maximum causal entropy, I do have time to provide some intuition and basic definitions. The causal part of the principle of maximum causal entropy simply means that we want to causally condition random variables on each other. In our context, this just means that the current action shouldn't depend on information from the future. For example, imagine developing a forecasting policy. Causally conditioned just means we shouldn't be able to condition on the fact that the agent is at the marked location at time t+2. The key idea of the entropy part of the maximum causal entropy is to not overcommit to any particular prediction more than the data forces you to. In particular, we'd like to minimize the surprise of actions subject to feature matching constraints. This idea is formalized by the notion of causal entropy. Here, whenever I say feature matching, I'm going to mean matching the satisfaction probabilities. So the forecasters that we use are going to be just as competent at the task as what we see in the data. To get some intuition about what optimizing this quantity would mean, let's consider the minimum entropy forecaster, which would put all of its probability mass on a single path. Then, if a demonstrator provides another demonstration, which is equally good according to the specification, but it is not this path, the agent would be very surprised. Conversely, the maximum causal entropy forecaster would hedge its bets and exponentially prefers high-value paths, but doesn't assign zero value to low-value paths. The key takeaway is that maximum causal entropy results in a robust forecaster. And this gives us an explicit way to answer this comparison of what's more likely, the left specification or the right specification. For our reduction, it suffices to consider linear rewards, where the reward is a linear combination of state features. Now suppose we observe or feature match to the expected value of the features. The principle of maximum causal entropy prescribes the following policy, where the Q and V values are defined via soft Bellman backup. The state value, V, is simply the log sum of exponentials of the action values, and the action value is simply the expected state value after applying the action plus the current state reward. This soft Bellman backup defines a family of policies indexed by theta. If one simply fits theta to match the data, Zbart proved that this policy is the one with maximum causal entropy. Finally, in order to complete our reduction, we need to decide what the reward should be. As we stated earlier, we'd like that a priori we shouldn't be able to distinguish between two traces that both satisfy the specification. A natural proposal then is to use the set indicator for the specification. We need to be careful though, because states are now traces. Consider the example on the screen. Let's add some explicit transition dynamics to make this a Markov decision process. Great. Now, consider a specification over lengths of trace 2. Lifting this MDP would result in the following tree. What's important is that states now correspond to paths in this unrolled tree. With this tree in mind, let's focus on the soft Bellman backup. For notational convenience, let's replace the log sum of exponentials with smooth max, denoted here by the symbol smax. Now, in the context of our tree, the soft Bellman backup corresponds to the following computation graph, where we've replaced f with the indicator function for whether or not the specification is satisfied. Here, we have a graph that takes as inputs either 0 or theta if the specification is satisfied, and alternates between expectation and softmax. Furthermore, it can be shown that the satisfaction probability grows monotonically in theta. Thus, in order to compute a maximum causal entropy forecaster that matches the demonstrator's competency, one can simply binary search for the appropriate theta. At this point, we could evaluate the likelihood of any given specification. However, in practice, this probably wouldn't be a good idea since these trees grow exponentially in the horizons, and thus even for toy problems, this would become quickly infeasible. We're going to leverage the following two observations to make this problem tractable. First, note that this tree has a lot of shared structure, and that most of the computation graph is redundant. This is due to the binary nature of rewards and the limited number of operators used in this expression. Second, we'd like to point out that the system and environment actions are ordered. Together, these suggest a natural encoding as a binary decision diagram of this tree, and will show that we're going to be able to adapt our soft Bellman backup to this binary decision diagram. We provide a summary of our procedure in the following figure. To begin, we take in a fixed dynamical system and a candidate specification. Together, these produce a binary decision diagram which induce a particular encoding on the demonstration as bit vector. In parallel, we take this binary decision diagram and we form a modified soft Bellman backup to compute the maximum causal entropy policy over this binary decision diagram. Together with the encoded bit vectors, these produce likelihood estimates that we're able to use to compare specifications. However, in the interest of time, we're going to focus on just describing the binary decision diagram encoding with the other details provided in the paper. Our binary decision diagram encoding centers around the following idea of modeling a Markov decision process as a deterministic transition system with access to NC coin flips at every single round. So for example, you can have a dynamical system that takes in state, an action, and some coin flips and produces the next state. Next, for simplicity, we're going to assume that the number of actions is the power of 2. This assumption is relaxed in the paper and we'll leave details there. Now, together with these two assumptions, we can write our dynamics as a function from state and a bit vector to a next state. Thus, using self-composition and composition with a specification, one can rewrite the entire unrolled tree as a binary predicate. As we proposed earlier, we're going to represent this predicate as a reduced ordered binary decision diagrams in the particular order that we're going to use, what we're going to refer to as the causal order, where the action bits precede the coin flip bits at every single time step. Given a fixed causal ordering of the bits, any predicate psi can then be represented as a unique, reduced ordered binary decision diagram, completing our encoding. A natural follow-up question then is, can you efficiently compute the maximum causal entropy policy on these binary decision diagrams? The answer ends up being yes due to 3 facts. The first is that softmax and expectation are associative. The second fact is that when softmax is applied with 2 identical arguments, this results in simply the argument plus a log2 factor. Similarly, when expectation is applied with 2 identical arguments, this acts as the identity function. This means that if we reinterpret our binary decision diagram as a computation graph, the associativity means that we can split the softmax operation across multiple bits, or the expectation operation over multiple bits, and if we have edges that are skipped over, we simply add a log2 factor for every softmax that's skipped over. Thus, the computation time is linear in the size of the binary decision diagram. A natural follow-up question then is, how big can these causal BDDs be? In the paper, we prove the following upper bound on the size of these causal BDDs. What's important about this bound is that it's linear in the horizon. Namely, the BDD can grow at most tau times the number of bits it takes to represent the actions and the environment actions, which are represented as coin flips, times the size of the composed monitoring automata, times 2 to the number of coin flips. Note then that using function compositions, one can build this BDD in polynomial time by incrementally unrolling the system. These size bounds have important implications on our overall inference procedure. Namely, after the BDD is produced, the encode, fit, and estimation steps are all nearly linear in the size of the BDD. This results in an efficient inference procedure for specification inference from demonstration. Finally, we validate our method with an experiment. For our experiment, we consider an agent operating in a grid world such as this. The agent can attempt to move up, down, left, or right. However, with probability 1/32, the agent will slip and move to the left. We provided 6 unlabeled demonstrations for the following task. Go to and stay at the yellow tile. We call that recharging. Avoid red tiles, so avoid lava. And if you enter a blue tile, which we call water, touch a brown tile before recharging. So this last one is informally known as don't recharge while wet. And do all of this within 10 time steps. And importantly, while 5 of the demonstrations are positive, the 6th demonstration, the one annotated as a dashed red line, fails because after it enters the water, it's unable to reach a brown tile due to slipping. We then ran our proposed inference procedure on a small concept class related to the demonstrated specification. We ran our inference procedure on the formula true, avoid lava, recharge, don't recharge while wet, and other conjunctive combinations of these formula. The demonstrated formula is the formula phi1 and phi2 and phi3. For each formula in our concept class, we computed several statistics such as the policy size, ROBDD build time, and the relative log likelihood compared to the trivially true formula. It's worth noting that the intended formula, phi star, has the highest relative log likelihood, despite the fact that there is an unlabeled demonstration error. By contrast, formulas such as avoid lava, which have no counterexamples in the provided data, have very low relative log likelihood compared to true. This implies that our method is able to be robust to demonstration errors, despite the fact that there are formulas that are exactly consistent with the data. If you're interested in exploring this data yourself or playing with our method, we've provided a hosted IPython notebook at the following URL. Furthermore, the code for this experiment can be found at the following GitHub repository. In conclusion, by leveraging the principle of maximum causal entropy, we've proposed a method for assigning likelihood estimations to demonstrations given formal specifications. This enables inference procedures that are noise resistant, unsupervised, and Bayesian. Furthermore, we provided an efficient implementation based off a reduction to binary decision diagrams. Finally, we've provided initial experimental validation of our method. Next, while in this work we've mostly focused on assigning likelihood estimates in order to be able to compare formal specifications, future work includes systematically searching for the most likely specification in a large concept class.
All right. Thank you, Masha.
Yep.
So the first question is from Maxi Weininger from TUM. I didn't get the point about the negative likelihood of the avoid lava property. It sounded like it was something good that it was negative, but I thought bigger was better. Is that column?
Yeah.
Could you please elaborate?
Yes. Can you hear me?
Yes.
Okay. Yeah, I have to double check what the particular ordering was, but negative, the relative log likelihoods negative is indeed less likely. And so the fact that avoid lava had a very negative value implied that it was much less likely than applying actions uniformly at random, if that makes sense. And the making it positive, I might have messed up the label there. Yeah.
Okay, thanks.
Mm-hmm.
So you mentioned that the finding of the likely specification will be future work. I'm just wondering what's a gap there. So you have figured out the properties, you have compared the likelihood. What's a gap towards finding
so
the
main problem there is how to systematically kind of propose specifications. So currently, what the system does is it takes a candidate specification. So you say, is this the specification? You can use any procedure you want to generate that. So you conjecture a specification and it gives you a likelihood. The problem is the space of specifications or trace properties is massive. And so I'm currently actively working on kind of systematically exploring that via a procedure where we generate gradients in this space, but it's very much future work still.
One more question from Lobna Goda. In the example you showed it take one path. Would it possible to take multiple paths?
In the example you showed, yeah, so it's possible. Currently, we assume that in that situation, our code and our kind of our method assumes that these are given IID, so they're not correlated. But it's possible to you would just simply add the logs of the probabilities.
All right, thank you very much. Let's move on to the next talk. Max Weininger is the next speaker, and he will talk about Automata Tutor version 3.
Welcome to our presentation of the tool Automata Tutor version 3. Our tool addresses a problem that probably all of us with teaching duties regularly face. It is good to let students do handwritten exercises. They learn more and personalized feedback is so valuable. However, classes are getting larger and larger, and it just becomes impossible to give good feedback to hundreds or even thousands of students by hand. We need something to help us teachers, something that allows students to get meaningful, personalized, but most importantly, automatic feedback. This is why 7 years ago, my co-author Loris, along with other good people, developed Automata Tutor. This tool allowed teachers to create some basic exercises on automata, and students could solve them and get automatic feedback. For example, here the student shall give a deterministic finite automaton recognizing all words that end with an AB. The student can try around and draw an automaton. So for example, this looks like it recognizes an A and a B, so let's make this final and submit. And we see that we made a mistake as we don't get full points. But not only that, Automata Tutor even points out where the problem is and gives us a counterexample. With this, we can fix our solution attempt, submit again, and we did it. It's correct. To this day, Automata Tutor has been used at more than 30 universities across 5 continents by more than 10,000 students, and it has automatically graded more than 350,000 solution attempts. And for every attempt, it gave personalized feedback with the same care as for all the others without any sign of exhaustion. Automata Tutor was well received. In fact, Luca Aceto even wrote an ode to the Automata Tutor, citing from that, "This is how the construction of finite automata that recognize regular languages should be taught in a modern way. I wish I had similar tools for all the topics I need to cover in that course." Well, today we announce that this wish has finally come true. We present Automata Tutor version 3, with many new exercises that teach concepts for the common introductory course on theoretical computer science. Adding to the deterministic and non-deterministic finite automata, now we have exercises on regular expressions, the pumping lemma, push-down automata, context-free grammars, and Turing machines. For all the new problem types, we still offer automatic grading and feedback generation, which is the central pillar of Automata Tutor. Additionally, to support teachers and to allow students to practice on their own, for some problem types we support automatic problem generation. So let's take a look at the tool to see how it looks in practice. This is the new Automata Tutor. Over here you have a collapsible overview structured by general topic where you see all the supported exercise types. Currently we are in this exercise, which is of the new PDA construction type. We are given the language a to the n, b to the n with n greater than 0. This box contains parameters like alphabet and stack alphabet, and this is a help box with details on how to solve this type of exercise. We have these for all types. Alright, so let's start drawing. For a to the n, b to the n, we need one state to count the a's and one state to count the b's. Here, we first want to put an A on the stack for every terminal A that we read. So let's add a self transition and tell it that when reading a terminal A and the initial symbol Z on the stack, it should push an A. This notation for PDA transitions is terminal, pop symbol / push symbols. It is reasonably standard, and if needed, we explain it in the help box. We also have to add that when there is an A on the stack, we want to push 2 A's. When the first terminal B comes, we want to go to our second state. Reading the B, we pop an A from the stack and push nothing. So let's see what Automata Tutor has to say about this solution. Oh, we made a mistake and we are missing some words, for example AABB. This is because we only pop one A when going to the right, but actually we have to pop all the A's. Let's add a self loop to the right state that pops all the A's that were aggregated on the left side. Now we submit again, and our solution is correct. Alright, so we saw that there are many new exercises and they give feedback and grades. Let's assume you as a teacher want to use the tool now. How does that work? After registering, on the homepage you can click the button Become Instructor and give us some information about yourself. After a short time, when we have granted your request, you get teacher rights, and then the homepage looks like this. Now you can create a course. Then, to allow your students and colleagues to join, you give them its name and the password. Inside the course, things look almost the same as before, apart from some management functionality and a plus button for every exercise that allows us to create problems. After giving the sample solution and some information about your exercise, you can finally create it. Then you still have to make it visible to the students by posing it. Here you can also specify things such as starting date and deadline. The new Automata Tutor has been used by more than 10 universities this semester, and it was used both this and last year for the big 1,000 student Introduction to TCS lecture here at TUM. Last year we conducted a survey and the feedback was actually better than expected. When we asked for the preferred means of learning, 3/4 of the students said they liked Automata Tutor, and it is the most preferred way of learning. The approval is higher than that of lectures, written exercises, and all the other things we offered. Summing up, Automata Tutor gives you a lot of possibilities to alleviate your teaching load, even more now that it supports exercises for so many important introductory topics. So if you are overwhelmed by teaching, or just interested, we suggest you try out Automata Tutor. We hope to reach both students and teachers around the world so that Automata Tutor makes their lives a little easier.
Okay, thanks. Very nice tool. We have a question from Tom Van Dyke. So are you planning to add Omega Automata to play with MBA, DBA, LTL, etc.?
Can you hear me?
Yes.
Okay, so I absolutely see the point, and we've actually played around with that. But right now, this is not at all our focus. Right now, it's difficult enough to just have the tool running for the universities, and like all the user interface, quality of life things and fixes that we have to do are taking more time than we anyway wanted to dedicate to this. But I guess, especially like if you're interested in the tool, then you can always ask us for the code and then extend it yourself or play around with it. And I guess that it might even be possible to, in a rather straightforward way, do this for MBAs and DBAs. I guess the most thing you would have to do is write the backend for that.
Okay, so my follow-up question is, if I can have the code and adapt it, can't I just adapt it to a cheating tool and to answer all the questions that's from Automata Tutor? And it's particularly relevant in the pandemic season.
Interesting question. So the code is not publicly available currently, so it's not like the students could get the code and cheat with it. And like the thing that is running at automatatutor.com is our version that certainly gives the does the correct thing.
Okay.
So yeah, as long as you're using our tool, then you're pretty safe that your students don't cheat. Pretty safe, I guess.
I see. All right. Thanks. It looks like Laura is already answering questions offline. So let's thank the speaker again and move on to the next talk, the last regular paper presentation from Priyanka Goria. The talk is about Manthan, a data-driven approach for Boolean function synthesis.
Hello everyone, I'm Priyanka Golia. I'm a joint PhD candidate with IIT Kanpur and NUS Singapore. I'm going to talk about Manthan, a data-driven approach for Boolean function synthesis. This is a joint work with Kuldeep Mead and Shubhajit Roy. So let us start with introduction to Boolean function synthesis. So here we have a Boolean relation f between set of variables x and y, where x is a set of n input variable x1 to xn and y is a set of m output variable y1 to y. For each output variable yi, our aim here is to synthesize a function psi that takes x1 to xn as its input. The bold psi represents a function vector such that if we replace y by psi of x in the relation f, it still holds true. That is, for all the valuation of x for which f of xy evaluates to true, f of x psi of x is also evaluates to true. Such a function psi I is called column function in the literature, and the process of deriving a function from a Boolean relation is known as Boolean function synthesis. So our objective here is to synthesize such a function psi. So just to ensure that we are on the same page, let us consider an example. So here we have x1 and x2 as an input variable and y1 as an output variable. And the relation between input and output variable is x1 or x2 or y1. We can call this relation as a specification also. So our objective here is to synthesize a function psi1 corresponding to the output variable y1. So let us try to rewrite this specification as negation of x1 or x2 implies y1. One can wonder, this negation of x1 or x2 can suffice as a column function corresponding to y1. So let us try to verify that. For that, first we have to compute f of x psi of x. So here we have replaced y1 with its corresponding function negation of x1 or x2. And as we can see here that for all the valuation of x1 or x2 for which f of xy evaluates to true, f of x psi of x is also evaluating to true. Hence, this is indeed a column function. But the question arises here is this the only possible column function corresponding to y1? And it turns out that there can exist multiple possible column function. That includes negation of x1 or x2 that we have just discussed, the negation of x1, negation of x2, and it can be just as simple as constant function 1. So there can exist multiple possible column function corresponding to a specification, and our aim here is to synthesize one such function. That's all about the introduction to Boolean function synthesis. Let us move to the application part of it. So the Boolean function synthesis has application in the wide variety of domain that includes certified way of solving, program synthesis, cryptography. We will discuss one such application, cryptography, in detail. The security of well-known encryption algorithm, RSA, depends on the factorization problem. So the factorization problem is, given a number x, we want to compute the non-trivial factor of x. So given an input x, we want to compute the output y, which is a non-trivial factor of x. For that, first we have to write this factorization problem as a relation between input and output problem. So here we have y divides x such that y cannot be the part of 1 or x as it is a non-trivial factor. Here, z represents a set of integer. So now we have a Boolean relation f, and we want to compute a function psi that takes x as an input and gives us y such that if we replace y by psi of x in the relation f, it still holds true. And we can do it by Boolean function synthesis. So that's how we can solve the problem of factorization via Boolean function synthesis. So our objective of this talk is to learn a technique to do such synthesis. So let us move to that. Let us start with state of the art. So the origin of this problem traces back to Boole's seminal work, which was subsequently pursued with the focus of decidability by a scholar. The problem of Boolean function synthesis has always been at the great interest of both theoreticians and practitioners. And over the decade, we have seen significant improvement on both the prospect. Theoretically, we know that there exists a problem instance where Boolean function synthesis must take superpolynomial time. Under the complexity theoretical assumption, P not equal to NP. On the other hand, the algorithmic improvement has been driven by a diverse set of techniques. Proof of the validity, the quantify institution in SMT solver, input-output separation, knowledge representation, incremental determinization are some of the techniques that were used in the recent year. Despite being intense algorithmic development over the decades, still there exists a good fraction of instances which are beyond the reach of state-of-the-art. We, as a practitioners, believe that we can do much better. So towards our goal of having better and efficient synthesis technique, we propose Manthan. Motivated by the success of machine learning, Manthan uses machine learning to come up with approximate candidate function. As we all know, machine learning needs data. Manthan does constraint sampling to generate the data. Later, the candidates are repaired using automated and formal reasoning. One thing I would like to emphasize here is, unlike traditional cigar approaches, Manthan learns approximate candidate function, which are later repaired using automated and formal reasoning. So it takes f of xy as its inputs. It first generates the data. With the data generated, it learns the candidate function. And it does a verification check on the learned candidates. Manthan is a sound system, and it will output a function psi only if the candidate passes the verification check. Otherwise, they need to undergo a repair iteration. Let us try to understand Manthan in detail. Let us consider each component one by one. So the first is data generation. We can consider the satisfying assignment of f of x, y as our data. But the possible satisfying assignment can be exponential in terms of cardinality of x and y. So we can sample uniformly at random from the possible solution space to generate the data. But the question arises is, if sampling uniformly at random is good enough to learn a function from a relational data? Let us try to understand this issue through an example. So here we have a specification between x1 and x2 input variable and y1 and y2 output variable. This table here represents all possible satisfying assignment for the specification f. So as you can see here that for a fixed valuation of x1 and x2, the input variable, we can have different valuation of output variable y1 and y2. That is exactly where it differs from the classical machine learning. In the classical machine learning, for a fixed valuation of feature set, we should have exactly one value of label. So if we ask to sample 4 data points uniformly at random from this possible solution space, we may end up getting this right-hand side table as our data. And as we have already discussed, for a specification, there can exist multiple possible column function. And for this specification, there exists a constant function 1 and a constant function 1 corresponding to output variable y1 and a constant function 0 corresponding to output variable y2. With this data, it will be difficult for machine learning to learn a simpler candidate function corresponding to output variable. Can we ask data to help the machine learning? So if we somehow be able to generate this data points, notice the change here. For all the valuation of x1 and x2, we have y1 equal to 1 and y2 equal to 0. So with this data, it will be easier for machine learning to learn a simpler candidate function. So here we hypothesize that just sampling uniformly at random is not good enough to learn a function from a relational data. So towards this end, Manthan proposes adaptive iterative sampling strategy. So it samples uniformly with respect to input variable x. At the same time, it biases the valuation of output variable y. So first it samples a small fraction of data with y biasing towards 1 and y biasing towards 0. With those data generated, it tries to find a good bias Q for the y variable. And then again, it samples uniform for the input variable x and with the bias Q for the output variable y. And that's how Manthan generates the data. Once we have the data, next step for Manthan is to learn the candidate function. So let us consider this specification and let us assume that this is the data we get from the data generation component of Manthan. Just looking at the valuation of y1, we can say that we can consider this problem as a binary classification problem. We can consider the valuation of x1 and x2 as a feature set and the valuation of y1 as a label. And we can learn the decision tree classifier with the feature set and label to learn y1 in terms of input variables x1 and x2. Let us try to generalize this. To learn a candidate function psi corresponding to an output variable yi, we can consider the valuation of x input variables as our feature set and the valuation of yi as our label, and we can learn a decision tree classifier with the feature set and label to learn the candidate function psi. So that's how Manthan learns the candidate. So once it has the candidate function, the next step for Manthan is to verify whether the candidates are the column function or not. So here we can have two cases. The first is when the candidate functions are not column function. So there should exist at least one valuation of x for which f of xy evaluates to true, but f of x psi of x evaluates to false. And if the candidates are this column function, then for all the valuation of x for which f of xy evaluates to true, f of x psi of x should also evaluate to true. So to check whether the candidates are this column function or not, Manthan constructs a formula E over x, y, and y prime variable. We call this E formula as an error formula. Let us try to understand this error formula. So let us look into the second clause of this error formula. So here we have the input variable x, same as the specification, but the output is different. So here we have y prime, and every y prime is fixed to its candidate function. So if the candidates are not the column function, then there exists a valuation of x for which f of xy evaluates to true and f of xy prime evaluates to false. And so this negation here will ensure that the error formula is set. And if the candidates are this column function, then for all the valuation of x for which f of xy evaluates to true, f of xy prime also evaluates to true. And this negation here will ensure this error formula is unset. So as a verification check, Manthan checks the satisfiability of this error formula. If the error formula is unset, Manthan returns a column function psi. So if the error formula is set, we have a counterexample sigma, that is the satisfying assignment of error formula to fix. So we know that when error formula is set, the candidate functions needs to undergo a repair iteration. But the question arises here is, out of m column functions, which one of those needs to repair? We know that when we fix the value of x to the valuation of x from the counterexample, f of xy evolves to true and f of xy prime evolves to 1. So all the pi variables where sigma yi is not same as sigma yi prime, the functions corresponding to those yi we can consider as a potential candidates to repair. So let us assume that psi I is such a function that needs to repair. So our aim of a repair iteration is to make sure that f of xy prime evolves to true with respect to current counterexample. So if psi I is giving us the output 0 with the current counterexample, we want it to give the output 1. And if it is giving us the output 1, we want it to give the output 0. So to repair its column function psi I, Manthan constructs another formula gi over x variable and y variable. So it fixes the value of x to the valuation of x from the counterexample and valuation of yi as per the output of the current candidate function. And it's tries to find the unset core of gi formula. Basically, it tries to find a reason why with the current valuation of x, yi cannot take the value as per its output candidate function. With the help of the unset core of gi formula, Manthan constructs a repair formula beta. And using the repair formula beta, Manthan repairs the candidate function. So that's how Manthan repairs its candidate function. So let us try to see the overall picture of Manthan in one frame. So Manthan takes f of xy as its input and it generates the data from the possible satisfying assignments of f of xy. With the data generated, it learns the candidate function psi with the help of a decision tree classifier. And it verifies whether the candidates are this column function or not. To do so, it constructs an error formula and checks its satisfiability. If the error formula is unset, it returns a column function psi. Otherwise, the candidate needs to undergo a repair cycle. So if the error formula is set, Manthan constructs another formula g over x and y variable. And it finds the unset core of g formula to construct the repair formula beta. And with the help of beta, Manthan repairs the candidate. And then it checks the satisfiability of error formula again with the repaired candidates. This loop continues until the error formula is unset. That's how Manthan does the synthesis of this column function. Let us move to the experimental evaluation of Manthan. So we compared Manthan with the state-of-the-art tool CADIT, PFSS, and C2SYN over 609 publicly available benchmarks from diverse suite within a timeout of 7200 seconds. So the plot here represents is a cactus plot with the y-axis being the CPU time and x-axis being the number of instances solved. A point xy represents that x many instances were solved by a solver in less than or equal to y much time. As we can see here that the state-of-the-art tool could solve at most 280 instances out of 609 instances. So where does the Manthan stand? So the green line here represents Manthan. Manthan is able to solve 356 instances, that is an increment of 76 benchmarks over the state-of-the-art tool. Not only just that, over a vis-to-vis analysis with each of these tools, it turns out that Manthan is able to solve 60 new benchmarks that none of the state-of-the-art tools were able to solve. Manthan is not only performing good empirically, but it also opens up several directions for the future work. So here we have hypothesized that just sampling uniformly at random is not good enough to learn a function from a relational data. But what is the ideal distribution to generate the data? We are still far to answer this question. We have found out that the candidate functions learned by decision tree classifier are good in terms of required number of repair iteration. But still we don't have any quantitative measure to measure the goodness of candidate functions. Last but not the least, can we use similar kind of technique to do the program synthesis and program repair? With this, I would like to summarize my talk. So we have discussed about Manthan, a data-driven approach for Boolean function synthesis. Manthan does constraint sampling to generate the data. With the data generated, Manthan uses decision tree classifier to learn the candidates. And the candidates are later repaired using automated and formal reasoning. With this technique, Manthan is able to solve 356 benchmarks. It also opens up several interesting questions for the future work. The tool is available online. Please give it a try. Thank you.
Okay, thank you, Priyanka. We are a bit behind the schedule, but let us try to answer the first two questions. The first question is from Chao Wang. I'm curious if the number of SYNTCOMP functions is finite.
I would say syntactically infinite, but as our truth table is finite, so there can be finitely many function mappings. So yeah, it's fine.
Okay. Thanks. The second question from Odette Patton. Can you comment on the connection to computational learning theory of Boolean functions? For example, the techniques based on Fourier analysis of Boolean functions.
I'm afraid I'm not be able to comment on that because I don't have a detail. I don't know more about this Fourier analysis of Boolean functions, so I'm afraid I cannot be able to comment on that. Sorry, I will look into that.
Okay. Okay, so for the interest of time, please answer the questions offline on Slack. Okay. All right, thanks again. Let's continue. We have the very last presentation from the Reactive Synthesis Competition, SYNTCOMP 2020. This is a virtually co-located event with CAV, and Sven Jacobs will tell us about the results.
Yes, thank you. Can you see the slides?
Yes.
Okay, great. Yeah, so thanks everybody for staying for the overtime. I will explain what SYNTCOMP is and what happened this year. So I'm organizing SYNTCOMP this year with Guillermo Perez from University of Antwerp. And so what is the problem that we're talking about? Actually, for SYNTCOMP, by now we're talking about 3 different flavors of synthesis. One of them, the first one that we looked at, so in all 3 flavors, you're supposed to synthesize what you can consider as a circuit B. And in the first flavor, you have given a circuit A, and you get some uncontrollable inputs U, and you're supposed to synthesize circuit B such that it reads U and the current state of the circuit A and produces controllable inputs to A such that an error output is never raised. So that's a safety synthesis problem. And then we have 2 other problems that start either from an LTL formula or the new one that we added this year, starting from a parity automaton that should always accept given what you get from B also. So that is essentially employing parity game solving. Why do we need SYNTCOMP? Well, SYNTCOMP, the idea was on the one hand to make it easier to compare synthesis tools. So we provide a common benchmark format and library, so everybody who's designing synthesis tools can use them for comparison. And on the other hand, every year we give a platform with a hopefully fair and comprehensive evaluation of the state-of-the-art tools in reactive synthesis. And the second idea is to guide a bit the development of synthesis tools. On the one hand, encourage implementation of push-button tools that work without user intervention. And on the other hand, to provide challenging benchmarks that people can aspire to solving. Historically, we had the first SYNTCOMP in 2014 at the Vienna Summer of Logic, only with the safety synthesis problem. Then 2 years later, we added the LTL track. Last year, Guillermo Perez joined as an organizer, and we did the migration to StarExec, to the StarExec execution platform. And this year we had a major, the first major addition since 2016, actually, adding this track that is based on parity automata that we're quite excited about. And we have also developed some tool support. All of this that happened last in this year, most of the hard work has been done by Guillermo, so big shout out to him for all his hard work. And we have some tools there that allow you to translate benchmarks from one format to another that help you setting up a parity game solver there for our competition. Okay, so what happened this year? What is this new track about? Who are the participants, and what are the actual results of SYNTCOMP this year? Participants this year, so we have these 3 different flavors. The safety track is mostly inactive. We ran 3 previous entrants this year again, one of them with bug fixes, but nothing surprising happened. So I will not go into the details of that. And then we have 2 interesting tracks. In the LTL track, we have 2 tools that received major updates. LTL Synt, that is a part of Spot, received a major update, and Strix, the winner from last year, also received an update, and both of them improved their performance. We'll see exactly what happened on one of the next slides. And then in the new parity automata track, we again have Strix because it uses parity game solving to solve the LTL synthesis problem. So they entered that part of their tool into the parity automata track. And we have a new participant, Tom van Dijk, entered his tool Knorr. And we will see how that turned out. Okay, so let's go into the results for LTL synthesis. We can distinguish between realizability and synthesis. For just realizability, so the tools only report a yes or no answer, whether or not the specification can be realized. Strix can solve the most problems, so it wins again this year. But LTL Synt, with its major update, comes closer than it did last year. So it improved more than Strix, comparing the 2 years. And what you see in parentheses here are different variants of the tool running. We allow up to 3 variants to run in every track. And then for synthesis, for the synthesis evaluation, what we do is we don't just count the number of solutions, but we compare the size of the solutions to a reference solutions, and then tools collect points based on that. And here the difference between Strix and LTL Synt is actually a bit bigger than in the realizability. That means Strix on average produces solutions that are a bit smaller than what LTL Synt gives us. Okay, and then in the parity automata track, Strix also was faster than its competitor Knorr by quite a margin actually. So Strix is the winner also in that track this year. However, we already had some interesting discussions after or while the competition was running. And actually, Tom van Dijk already gave us a new version of his Knorr tool that uses BDDs to symbolically solve a part of the problem or represent a part of the problem. And that is much faster than anything else. Yeah, also note here, what we give here is the time that is required to solve all the problems in contrast to what we have before. And you see here that this is quite a low number. So the benchmarks this year were too easy. That's one of the things that we need to look at for the next years. And we don't have a synthesis comparison here because Strix is currently the only tool that allows to really synthesize a solution. Okay, and that's it. As a quick summary, we this year had a successful first iteration of the new parity automata game track. More benchmarks are needed, more difficult benchmarks are needed there. Also, we need more tools that support synthesis. We plan to revive the safety track with a focus on synthesizing safety shields. That has been a big thing in recent years. Yeah, and on the right-hand side, you again have the winners. And that's it. Thank you.
Okay, thank you, Sven. Okay, I just saw one question on the thread. Just a follow-up question to a discussion during Synced. Considering that for gathering the P-game benchmarks, you use the LTL synthesis benchmarks, and most of these timed out, so no parity game was generated. Would it make sense to extract benchmarks from partially translated LTL synthesis benchmarks? Considering that from earlier version of Strix, we have parity game examples of 30 million vertices.
Yeah, that might actually be an idea. If we can get these intermediate results of the translation, we could just take whatever is ready. I mean, I assume that we can do that. We can at least try. That's a good idea. Yeah, I think that's an option we should look at. Yeah.
All right. So so can you add more about how the current benchmarks are from? How do you collect them, and do you do anything to guarantee the diversity or?
Yeah, I mean, so we have benchmarks from various sources. So participants of previous competitions submitted their benchmarks, and some of the benchmarks were also submitted from other people working on synthesis problems that did not participate in the competition. So most of them are generated by people working in the field. We also have some randomly generated benchmarks. We have some benchmarks that are modified from the hardware model checking competition. So we have a quite diverse set of sources, I think. But of course, having new sources would always be better.
All right. Okay. Thanks. I think that concludes this session. I think the breakout session is already happening. So feel free to join and hang out with your fellow participants. And thank you all for joining this session. Have a nice day. Bye-bye.